Thank you so much for having me and for allowing me to be the next speaker in the SpaceML speaker series. My name is Anna Jungbluth, and I am a PhD candidate at the University of Oxford in physics. But I have been part of the FDL for the past 3 years, first as a researcher and then as a team lead. Today, I want to talk about our FDL 2019 project on super resolution. And for this audience, I want to demonstrate a converter that allows you to perform super resolution of solar magnetic field images. And I'm very happy to answer questions at the end of my talk. So let's start with a quick overview of my presentation today. First, we'll start with a summary of the project, and then I'll move on to discussing why studying the solar magnetic field is interesting. I'll provide some background on the different instruments that have taken images of the solar magnetic field, like the image that I'm showing you here on the right. And I want to talk about the specific instruments that we decided to focus on in our project. And next, I'll provide some background information on the data processing steps and technical details that were involved in training. And finally, I'll show a short demonstration of how to use our converter. So let's start with a quick summary of our project. Magnetic field images, known as magnetograms, have been measured by many different instruments. And these instruments all observe the sun at varying cadence, resolution, position, and with very unique instrument characteristics. And while observations are plentiful, long-term space weather studies often require consistent data sets that span timescales beyond the lifetime of one instrument. So the solar cycle is about 11 years, and ideally we would have data that spans multiple solar cycles. The amount of data, so more than 50 years of observations that we have, is of course ideal for computer vision and machine learning applications. While magnetograms are very easily and freely accessible, the pre-processing often requires very specialized scientific knowledge, and combining all of these different data sources into one is very challenging with traditional analysis techniques that are not based on deep learning. So to address this challenge, we have created a super resolution converter, which is a cleaned code base with our best model and data processing functions. The model was trained on overlapping observations of 3 instruments, and I'll talk about the instruments in just a second. It allows users to perform inference on raw magnetograms and low resolution images to super resolve and cross-calibrate, imitate the characteristics of the high resolution mission. So let's talk about solar magnetic field observations. On the right, you see a magnetogram from the helioseismic and magnetic imager on board the Solar Dynamic Observatory. Here, the colors represent the strength and the direction of the magnetic field, with green and blue representing an outward magnetic field, and yellow and red representing a negative inwards magnetic field. The sun has features across a wide range of spatial and temporal scales, and here you can already start to see clear regions with strong positive and negative magnetic fields. These are known as active regions. In addition, you can see a sort of gray underlying background of the quieter parts of the sun that, if you zoom in, show an almost salt and pepper or fractal-like structure. We can compare this magnetogram to images taken by AIA, which is another instrument on board SDO. And this image here on the left shows you the corona and flare plasma. And here you can see that the regions with strong magnetic fields act as an underlying driver of the solar flares. And this highlights just how important it is to understand the solar magnetic field as a whole in order to understand space weather and how it might affect us here on Earth. The prediction of solar flare occurrence is an unsolved problem in heliophysics. However, having a consistent long-term data set could bring us closer to solving this challenge. So let's take a closer look at some of the different instruments that have observed the sun. Scientists have of course been fascinated by the sun for centuries, and many of the early measurements were drawn by hand. But over the past 50 years, we have had a lot of observatories and space-based missions taking images of the solar magnetic field. Here, I'm highlighting a few of these instruments and how long they were taking measurements. After each instrument, in parentheses, G signals that these observations were done on the ground, and S signals that the mission was space-based. One of the big differences between spaced and ground-based observations is that on the ground, atmospheric distortion plays a role. And just with any good camera, with time, technological advancement has led to substantial improvements in the quality of the images. The highest resolution images today are taken by the Solar Optical Telescope on board Hinode. However, these images are not full disk, but focus on specific regions of interest of the sun. And the highest resolution full disk images that we currently have available are taken by HMI, which I introduced earlier. I wanted to show you a video of the same area of the sun as imaged by the different instruments. And these images were all taken on the 1st of April, 2011. And the resolution difference here is really quite striking. While some of the older instruments aren't able to resolve small scale features at all, newer instruments provide an impressive amount of detail. And in addition, you can begin to see some of the other instrument differences, such as the differences in the underlying noise floor. During our FDL 2019 challenge, we decided to focus on 3 instruments in particular. I've already mentioned that HMI provides the highest resolution full disk images, so that's why it was chosen as our high resolution target mission. As our lower resolution input, we chose the Michelson Doppler Imager, MDI, and the Global Oscillation Network Group, GONG, which is a collection of 6 ground-based observatories. After HMI, MDI provides the next highest resolution full disk images and reaches all the way back to 1996. In the interest of time, my talk today will focus on the MDI to HMI conversion, though our converter also works for GONG to HMI. MDI and HMI overlap for 1 year, from 2010 until 2011, and this leads to 9,000 magnetogram pairs. While this might at first not sound like a lot, these images are quite big, so they can be split up into patches, and that led actually to millions of training samples. The resolution difference between the 2 instruments is a factor of 4, so HMI produces images that are 4K by 4K, while MDI images are 1K by 1K. In addition to increasing the resolution, instrument differences need to be accounted for as well. Here in the images that I'm showing, the full disk and the little insets, the zoom-in patches, you can very clearly see that the underlying noise floor is quite different. And in the MDI images, we see a green and grayish background. But in addition to that, they also have different instrument orbits, positions, etc. So the goal of our challenge was to do super resolution and instrument cross-calibration to take these characteristics into account. For the super resolution component of our work, we can make use of an extensive body of literature, and a lot of super resolution work was published on natural images, like the work by Dahl et al., which super resolved human faces impressively well from barely recognizable collections of pixels. But to talk about the cross-calibration component a little bit, I wanted to show a little example. This is a headshot of our wonderful team lead Andres and what he looked like at the beginning of the FDL summer. And we were joking that this is what he looked like after working with us for 8 weeks. But jokes aside, in this example, we use a program called FaceApp to transform what young Andres might look like when he's old. And this is done by using our previous knowledge of how different facial features change with age. And so this example highlights quite nicely how it works when we try to imitate what a measurement would look like if it had been taken by a different instrument instead. So let's talk about data processing and model training. More information on the technical details of data processing, ML architectures, and experiment validation can be found in our 2 NURBS workshop papers that I've linked on the right. We're currently doing revisions for a journal publication that provides additional information on our approach, and this paper should be published within the next few months, so keep your eyes open. But to talk a little bit about data processing, we performed a number of steps. So first, all images were rotated to solar north. We tried to temporally align our images as best as possible. Of course, the measurement cadence between the different instruments was not the same. We also tried to standardize the size of the sun to account for non-circular orbits of the instruments. And we tried to align all the features through registration and XY shifts. My colleague Paul wrote a great Colab notebook that visualizes our data and pre-processing steps, and that notebook can be found on the SpaceML website. In addition, we decided to split each full disk magnetogram into 1,024 patches. And our ML input consists of both a magnetogram and a location layer, where the location layer specifies the distance of each pixel from the center of the solar disk. This was important because the line of sight measurements that we're working with show 2D images of a 3D object, and we expect to see some projection effects around the limb. So taking location information into account will help us understand how well our model is able to handle these projection effects. A sample of our aligned and processed patches is already publicly available on Google Cloud, but we intend to make the whole data set available for use as well. Without going into too much technical details, we tried many different state-of-the-art super resolution algorithms, but the model that worked the best for us was an adaptation of HiResNet developed by Element AI, and the original paper is linked at the top. HiResNet is based on an encoder-decoder architecture with a bilinear upsampling and a final convolutional layer to perform the trick. And yeah, without going into too much technical detail, I just wanted to introduce our model since it provides the backbone of our converter. So now finally, let's look at a short demonstration of our converter. The converter is currently hosted on Zenodo and linked on the SpaceML website. It contains a cleaned version of our code to perform inference using our best model, and also has all required functions to process and prepare the data, so users can start with raw magnetograms that they can download online. In addition, all the checkpoints and weights and biases of our best models are provided, and we continuously update the Zenodo repository as we're iterating through our project. On SpaceML, we have provided a short notebook to demonstrate how to use the converter, and it shows you how to set up the notebook, download the MDI data from Stanford hosting platform. But to jump right in the middle of it, the converter can be easily run in your terminal, and instructions to that are provided on Zenodo. But if you prefer to use the converter in a Jupyter Notebook environment, we show you how to download the converter into your Google Drive and access the Python files from your Colab notebook. And in addition, we are providing information on how you can download and save the MDI images, either into your Colab notebook or your Google Drive, shown in cell 11. Finally, to run the converter is just one line of code, shown in cell 13. It takes a number of different keyword arguments, and these can also, and more information on these can also be found on the Zenodo website. For one, you can specify which mission you're hoping to convert. As I've mentioned earlier, we currently have the functionality to convert MDI or GONG to the resolution and characteristics of HMI. You can specify the data folder where you like the output and where you like the output to be saved. And in addition, you can decide if you want to perform inference on patches or the full disk images. Both work well, but full disk operations tend to take a little bit longer. Finally, in cell 14 and 15, I'm showing you how to visualize the results, where on the left, we see the low resolution input, and on the right, we see the ML super resolution output. But because this isn't doing our work justice, I wanted to highlight the immense improvements a little bit more strongly and finish by showing you a comparison of our input, target, and ML output. And here you can very clearly see the MDI's green and gray noise floor was successfully removed. And in addition, a lot of the features of the active areas are now substantially sharper and better defined. To finish with a summary, I presented a magnetogram converter that can be found on SpaceML. The converter consists of a cleaned code base to perform inference using our best model. It allows users to super resolve and cross-calibrate magnetograms taken by MDI, GONG, and HMI. I also presented a short notebook to demonstrate how to use the converter. And on the right, you will find links to some of the resources that I mentioned throughout this talk. SpaceML is a machine learning toolbox and developer community building on open science AI applications for space science and exploration. And you can find out more at spaceml.org. Of course, none of this work would have been possible without the generous support of NASA, the SETI Institute, and all of our other wonderful academic and industry partners. And this work was obviously a team effort, so I will leave the names of all the wonderful people that contributed as my last slide. And with that, I would like to thank you for your attention, and I'm very happy to answer questions.
Thank you, Anna. That was amazing. So I think we've got a few people with questions lined up. Freddie, I believe you had a couple that you wanted to ask. So can I pass over to you, please?
Thank you. Yeah, Anna, thanks for the talk. That was good. This is a super resolution approach that gives you a higher definition, higher resolution image based on a single low-res image. So this is an example of what a lot of people call an inverse problem, where you try to well, some of them call it also ill-posed problem. That's because there are many solutions, potential solutions to super resolution. What mechanisms are put in place to constrain the space of feasible solutions that are compatible with the lower res program?
Yeah, so that is, of course, an excellent question, and something that we were thinking about quite a lot throughout the development and execution of our project, because at the end of the day, the work that we do is only as valuable as the output might be to some of our domain experts and collaborators that want to use our work in their future research. So throughout our challenge, we have defined different loss functions that we're employing that try to constrain some of the physical parameters that we might be interested in. So one thing we know about the magnetic field is that it has to, sum up to 0. So this is something that we were taking into account. We wanted to track high strength magnetic fields. So all of these components kind of ended up influencing the way we set up and designed our pipeline. But in our journal paper and other papers, we go into a lot more detail on some of the performance metrics that we applied to be able to verify that our approach makes physical sense. But of course, something else that I wanted to bring up, and that I'm guessing other people might have questions about as well, is that this work really needs uncertainty quantifications. And one of our NURBS papers was precisely on this topic, and we're still working on expanding that work. But of course, when you provide these images to users, ideally you would have some sort of uncertainty quantification of how sure you are that the result that you're providing is physically accurate, and exactly what you were saying, that it's not a one-to-one mapping actually based on a low resolution input. There might be a lot of different super resolved outputs that provide a realistic version of what the mapping might look like. So yeah, definitely have a look at our NURBS publications, but this is also very much work in progress. And to plug one of the other SpaceML projects and one of the other FDL challenges, we had a research team last year looking at super resolution of images of the moon, and they have also spent done some amazing work on uncertainty quantification.
Hi, I'm Lavnish. I have a question, if no one does. Can I go for it?
Yeah, go ahead.
Yeah, okay. Hi, Anna. Great talk. I was in Moon for Good team in 2020. The question I have, so first of all, I'm not from machine learning or AI background. I'm from the space domain. And if I'm not mistaken, you also come from the physics domain. So my question is more from the application end of the output. So with these super resolved images, was there some additional information or some additional information about the physics of the problem that could be obtained or that was obtained in terms of the value of the work and deducing something that could not be from the previous from the input, let's say?
Yeah, so one of the things that we were able to quantify quite nicely was oscillations that you were able to measure, like instrument characteristic oscillations that we were able to observe in the lower resolution images of MDI that we were able to remove in our super resolution input. So I might redirect this question to Paul, who's one of the domain experts in our for this project. But this is just one simple example where we were able to remove some of sort of the intricacies of our lower resolution data that might come in the way of performing data analysis approaches that were relevant for the physicists. But I really wanted to also use this as an opportunity to say that we are strongly inviting collaborations with other domain experts and physicists who might be interested to use our data to run their analyses programs on it, so that we can figure out how good we're doing, if our data is satisfying all of the needs of our expert users, but also so that we can finally provide this consistent data set that I was speaking about before for long-term space weather studies.
Okay, thank you. I had one other question, and this was now more about the process, rather the process itself. So is there, say, do you guys see any, I want to call it spin-off, for, I cannot think of another better word, of the process itself. So so you put together a process from input to the output. Now, can that process be taken and applied in some other application?
Yeah, so I mean, in principle, we have demonstrated that, you know, this work is feasible to do on scientific data. So whatever data you want to pick, if it's images of the solar magnetic field or something different, you can apply these approaches. But the reason why I highlighted many times that we had a super resolution and an instrument cross-calibration component is because either one of these are interesting for scientists to do. So a lot of the previous work that has been done on super resolution of solar magnetic field images was done on downsampled versions of the images themselves, so just the super resolution part. But even if you weren't interested in increasing the resolution of your images, you might be interested just in the cross-calibration component. So this is definitely something that would be amazing to continue working on or collaborate on with other people interested in this work, if a similar approach might be relevant to their scientific research questions.
Okay, that's great. So in essence, if I understand it correctly, this could not exactly replace, but complement, say, just even something like calibration of different instruments.
Yeah, possibly, yeah.
It doesn't need to be, say, limited to solar imagery. It could
not
be
at all,
to...
not at all. It could also be, you know, applied to Earth observation informations to study the effects of climate change and lots of different applications, which of course the FDL is absolutely having their hands in already, and, you know, having these amazing challenges happening each individual year. And then of course, just coming back to the discussion that we had with Freddie before, uncertainty quantification for these types of applications is of utmost importance. So that's something that we're currently still working on, but would also invite other people to tackle.
Perfect, great, thank you.
I've got a question.
Yeah, go ahead.
One back in Earth observation, one value of enhancing Earth observation or super resolving or downscaling, as people call it in the Earth sciences, is using being able to downscale simulations at a smaller as a subgrid level, by using either like data that come in very high resolution, or just applying directly super resolution techniques on what a model-based approach does. So in a lot of times we have this like synergy between simulation, numerical simulations, and data-driven approaches to fill in the gaps of what we can't use physics for. Do you suppose in the future there might be something similar happening for the sun by using this high resolution magnetograms?
Yeah, so I think some of this is already happening, that people have used simulations to complement their super resolution approaches. So that's definitely a very valuable approach to do. We didn't consider it for this project, but maybe Andres has something else that he would like to add to answer this question more fully.
I don't want to change the focus from you to me, but yes, these are things that people are looking into right now, and there is a whole field of potential potential innovation when it comes to simulations following that idea. But now that I'm talking, I want to ask a question to Anna. So if someone is going to do this kind of work in other applications, maybe you did this about the sun in magnetograms, but there are other imagers in other fields that can benefit from something like this. What do you think are some of the valuable lessons that you would like to share, that you would like perhaps to know, that you will tell to yourself when you started doing this kind of work?
Yeah, so that's an excellent question. I think one of the main amazing takeaways from the FDL is that none of this work is done in isolation, but it's done in collaboration with incredible people who have very valuable things to add. So for people in positions where you might be the sole lead on a project like this, try to get as many people from the domain and ML side involved early on, just so that you can identify where you can save time and avoid reinventing the wheels. And of course, as a shameless self-plug, our project can be used as an example for that. So even if all of our code might not be 100% applicable to your specific research question, feel free to recycle some of the functions that we've written, because some of these are not, they're not specific to heliophysics challenges, but they're just general data processing and alignment type functions. And yeah, of course, the strength of the FDL is to bring people from all sorts of backgrounds together to create something truly unique and groundbreaking. And so that's something that I will take away with me for the rest of my scientific career. So I can only highly advise other people to do the same.
That's amazing. Thank you, Anna. Unfortunately, this is all we've got time for this session, but in case you have any further questions, also for our viewers who are going to be viewing this video, we will be holding office hours with Anna in about a month's time, and there'll be more information coming out for that on the SpaceML newsletter. These office hours will be held over Slack, so it's really easy. You can just start up a conversation. You don't need to be on video if you don't want to be. And, there'll be a window which will hopefully apply to the greater part of the world time zones. We'll do our best. But thank you so much, Anna. This was really informative, and I think everybody enjoyed hearing you speak and learning about this project. And we look forward to seeing everybody for episode 3 soon.